feed via my phone on YouTube and see if the stream's reaching it. YouTube, Utah Rust. Really need a dedicated AV guy, so I have to do this all myself. Utah Rust, because I am not an AV guy. I'm just pretending to be one on YouTube. All right, where is the live thingy? It's showing me the old stuff. I want to see the live stuff. I guess I go to Utah Rust itself. Live. And it has the wrong title on it. Where did it get the title from? Honestly, I don't even know where it got the title from, but let's see if this works. Hey, I can see you. Okay, if I turn the audio up, do I get some...
Hey, it's like magic.
Hey, it's all working. Okay. So, we've got the stream hooked up. We've got Zoom hooked up for people attending live. Stop playing, phone. Okay. All right. Taylor, I'll go round up the people outside and we'll get started.
Sweet.
All right, folks, we're ready to start. You're welcome to finish your pizza in here or finish out here in that hand, but we're going to start in about 60 seconds. Okay, well, any Rust people out there? Okay.
Yeah. These iguanas are...
Wow. Looks like a lot of people are interested in AJ's Zig stuff. Cool. All right. We'll just give it like a minute just in case anybody else wants to come in here. And then we'll get started. Okay. I think Spencer's coming.
Guess we'll see him.
He opened the door and then went back. I think he forgot his backpack or something. All right, when Spencer comes in, we'll go ahead and I'll do the big official intro thing, and then we'll get started. And yeah. And then if I'm gonna leave and come back for a quick moment, just ignore me, okay? Just keep going.
Sounds good.
All right, Spencer, guess you're the last one in.
Yeah.
We'll see if I ever wear a tie again, scaring
I'm so sorry.
Alrighty. Welcome everyone to Utah Rust, the meetup. Hope you all enjoy the pizza. And we've got Taylor Allred presenting tonight. Thank you, Taylor. I'm your host, Nathan Stocks. I don't really have anything to go over myself today. So I'll just go ahead and turn the time right over to Taylor. Take it away.
Awesome. So, arena allocation is my talk. I'm Taylor Allred, and as we go about this talk about arenas, you might have questions. That's awesome. I may or may not know the answers to those questions. I'm not an expert in this topic by any means. I am just a nerd who has been exploring and seeing the possibilities. So let's learn together and just kind of explore the space, huh? Speaking of exploring, I love to explore in the world of programming languages. I like to go to different places and see what they're up to and how they approach different problems. I've been to the academic ivory towers of Haskell. I've meditated with the monks on the crested slopes of Lisp. But I've, of course, found something of a home in the industrial town overlooking the crab-infested shores of Rust.
Did you make these in AI?
Yeah, these are AI generated.
Did you generate them?
Yeah, I generated them.
That's so cool.
Yeah. Did you notice there's parentheses in the Lisp hills? That was by design.
That's fantastic.
One day I decided to go on a trip to the ancient city of C. And quite like visiting any ancient city, you realize that it's things have changed since then. You don't go to Rome and see centurions walking around and gladiatorial battles. And so in the C world, I was intrigued that they had been doing things a bit differently than the way that I had seen C done in school. And so I'm hanging out with them and I ask, so what are you guys doing about memory these days? Because I remember that was hard back in the day. And they turned around and they pulled out this thing called an arena. And I was intrigued. So before we talk about that, let's just review memory. And I would argue that memory is kind of the reason we're all here, huh? It's the reason Rust even exists. The thing about memory is that we need it. We need to put things into our computer's memory so that we can work with it. And the trouble is, how do we get that memory out? And the first solution to that problem is really simple, and it's just the stack, right? So just to quickly go over how a stack works, we have this stack of memory that grows downward. There's a stack pointer telling us where we can allocate the next bit of memory. And we call a function, we allocate a bunch of stuff, increments the stack pointer, and then when we return from the function, we just move that stack pointer right back to where it was. And all that stuff is still there on the stack, but it's going to get overwritten by the next function call. So really easy, really simple, and it models directly into this model that C gave us of scopes, where you create a scope, you create local variables, and then out of that scope they all just get freed. Really simple, not even really a problem. The problem comes when we need to do heap allocations. And the reason we want heap allocations is, well, what if we don't quite know at compile time the size of something? And so we need to dynamically allocate memory. What if we want the lifetime of something in memory to last longer than a stack frame? That's when we need the heap. Now we need to figure out how we're going to get rid of that. So let's just go over a couple of strategies that have existed for getting rid of stuff on the heap. So the first one is, what I learned back in school is what you do in C, which is you run malloc, tells the operating system, hey, go allocate some memory for me. It gives you back a pointer and says, hey, here's your memory. And then you're responsible for telling the operating system to free that memory when you're done with it. And with that, you just call free. This is the classic way it's been done, and there's a lot of problems with it. Namely, sometimes it's hard to know if you're the one responsible for freeing a pointer. What if somebody else is referring to it? Has it already been freed? These kind of memory issues are pretty typical when you're working with C in this way. And so, over the years, people come up with various solutions to this problem. The first one that we all know is garbage collection, right? In a garbage collected language like Java, if things on the heap get to the place where nothing's referencing them, they're just hanging out there on the heap until the garbage collector comes along, stops the execution and says, hold up, I'm going to go check to see if there's any garbage. It does this crazy algorithm that many smart people have worked on for years, and it goes and cleans things up for you, and then tells you to continue running your program. So that's the first thing, and a lot of what we do today uses that. Another solution is Rust. Rust says, okay, remember that problem of trying to know who's responsible for freeing memory? Well, let's just say that every value can own memory. So if there's something on the stack that owns something on the heap, then when that memory goes out of scope on the stack, then it will automatically go and free it for you. If there's something on the heap that owns something else on the heap, then when that gets dropped, then it has to drop all the things it owns. And so we have all this really difficult concepts to learn to understand how the borrow checker works and how ownership semantics work. But it's a really useful model to have in your head to think about responsibility and what's the lifetime of an object. And it's one of the reasons we love Rust, because it just deals with these memory problems. Another one that I almost forgot about was automatic reference counting. This is where you actually add a number to every heap allocated object that says how many things are referencing it. And every time you add another reference, it will increment that reference count. And every time a reference goes away, it will run codes to go and decrement that counter. And when that counter gets to 0, then it knows that it's time to free it. This is something that is famously used in Swift. And if we're using Rust and we're using the like arc or the RC type, then we're basically doing the same thing, right? We're attaching a ref count to a heap allocated object. And this is really nice when you just don't know, how many things can be referred to an object, and you don't really want to manage that yourself. So it's just like, all right, once nobody's looking at this anymore, get rid of it. Unfortunately, this is actually a really slow option. Just anecdotally, some benchmarks that I've looked at and talked to with PhD type people is that doing just kind of classic garbage collection tends to be faster than automatic reference counting, which is really unfortunate because I like this solution a lot. There's another solution, and I must warn you that this might be distressing for some people in the audience. Just leak. If you're running a program that just does some stuff and then exits, you can just leak because the operating system is going to clean that up for you. It's its job to clean up the memory of a program after it's exited. So that's a totally viable solution. If you're ever running C again and you just have a little utility like cat or ls, kind of thing, you can probably just leak it and you'll be fine. No need to worry about it. So anyway, there's some traditional memory management ideas. But now let's get on to the topic of this talk, which is arena allocation. So this is another approach with the problem. And the idea is, and here's some code in C, illustrating it in its kind of simplest form. The idea is that we actually create an object of sorts called an arena that will go, when we make an arena, it will go and just get a whole chunk of heap and say, okay, here's the whole heap we're going to work with. And then it has an interface to allocate objects onto that arena. So in this case, we're going to allocate 512 bytes, and we get a pointer back to P1, and then we're going to allocate 64 bytes, and then we're going to do 1024 times 1024. And so we have these three pointers to things that are allocated on the heap. But instead of freeing them all individually, when we're done with it, we just run this function called free arena, which will go and free everything in that arena. And so what we've done is we've actually kind of packaged up allocations that go together, as it were. They all have the same lifetime. They should all be in memory at about the same time, and when we're done with them all together. That's kind of the mental model of an arena allocator. As you can see here, so we have like a start pointer saying, okay, here's the beginning of the arena, and then as we push stuff onto it, we grow this next pointer, which the student in the audience will notice looks a lot like a stack, because it's basically like a stack that can outlive a stack or be passed around to other stacks. Here, so some particularly good use cases for an arena allocator is a server. You could have a server where each handler will just create an arena right off the bat, and then every allocation it does throughout the handler computation will just allocate to that arena, and then when it's done and it's sent its response back, it just frees that whole arena. That's a really easy use case for it. Another one is game. You could create an arena for every frame. Just do all your allocations, calculate your frame, and then at the end of it, free everything that you did there. It's things that go together. Another really useful thing, and you're going to notice that this is super useful for Rust, is any data structure that is very pointer heavy, where things can point to lots of objects like trees, even graphs where you have interdependencies. You can just create one arena in which you can allocate every node of this data structure that within it has lots of pointers to each other, but goes together as a unit, so you can say when you're done with it, all right, free that whole data structure. And I'm not going to go chase down, who owns what and who's responsible for it. I'm just going to say this all goes together and it all gets freed together. Any questions before I go on? Is this making sense?
Sounds good.
Sweet. Well, moving on. I really recommend this article by a programmer named Ryan Fleury. He's a engine and tools programmer at Epic Games. And he has this article called Untangling Lifetimes, Arena Allocator, where he basically says that when writing C code, he just uses arenas for everything. Like that's the only thing he uses. And some people kind of argue with him on this, like, what do you mean? Like you use it for everything? And he's like, yeah, like it works. And the way he kind of goes about it is, okay, if I have a function and it needs to do some allocations, I just make a scratch arena right off the bat. I do all my work, and then at the very end of that function, I just do a little free. And if I need to have a function that allocates memory and has to return its allocated memory back to the caller, well then I make that function take an arena as a parameter. So this is like basically saying like, hey, I allocate and you're responsible for it, so give me a place to allocate it to. Question?
So, I don't understand how arenas work, but is it everything inside there, is that all allocated like into that thing basically, like lines my struct and all things below, and then you free everything at the end? Or is
Yeah.
Really?
Yeah.
So is that easy?
Is that easy?
Well, that sounds easier than
I know it's.
for.
So here's the thing. I haven't like done what this guy Ryan has done, which is like write whole applications in C using arena and anger. But I have used it to a certain degree, and yeah, it's pretty easy. You make your arena, and then you arena allocate all your stuff, and then when you're done with all that stuff, you just run free. And so you kind of create this you're basically doing the same thing that Rust does, right? With Rust, it's like on a per value basis. Like, yeah, this thing owns this data, and it has this lifetime. What we're basically saying is that, all these things go together in the same lifetime, and so we're going to free them at the end of their lifetime. Kind of make sense? Another question?
Yeah. So for the arena free at the end,
Mm-hmm.
could you just avoid that entirely if you just did the RAII nonsense?
Yeah. So if you're like in C++ or even Rust, which we're going to see later, and that arena just going out of scope,
Yeah.
right, would call whatever code it takes to drop all that memory. Absolutely, yeah. If we're in C, then we have to call it explicitly, or else that arena is going to that heap allocation is going to stick around, even though our arena that's on the stack, that's like our, the arena on the stack is just a struct with pointers, right? So that will go away, but the heap allocation will stick around because it just, it just did a page allocation. And so we have to like explicitly say, hey, arena, you're done, go free your memory.
So you just pass this arena everywhere throughout the thing, and then like suck it
Yeah.
all up.
Yeah, you just like pass it in, and because like that's the thing. Hey, you have this function that's like, hey, I allocate, and you're responsible for it. So give me a place to put it, and I'll put it on your arena, and return you a pointer to what I allocated. And sometimes you can have functions that have two arenas, so the one that was passed in and the scratch arena that they allocate, that they free at the end of their scope. And then they just pass back whatever they allocated onto the passed in arena.
Yeah.
If you can kind of picture that.
So can the arena have multiple different types in it?
Yeah. So in this, so here we're going to learn later that there's lots of ways to implement this
Okay.
idea. There are ways to do it where it all has to be the same type, and there's ways to do it where it can be any type. And there are different trade-offs, and we'll look at those.
Is the memory for Arena, do you usually try to keep it contiguous, like you pre-allocate a big chunk, or does it just have
Yeah.
a bunch of pointers to...
So again, there's lots of ways to implement it, but like a really simple way to do it is basically implement it the same way that a standard vector is. right? Standard vector is just an array in memory, and you just kind of allocate a chunk up front, and when you get too far, you reallocate with twice the amount, and just keep going like that. You can implement an arena very much the same way.
Just a simple question. Where does the term arena come from? Like, why do they use arena?
I don't know. There's lots of names for this concept.
Yeah.
It's from
Uh,
Nintendo, Smash Bros.
Yeah, it's the arena fighter genre. Yeah.
Is a slab allocator the same concept? Is that a different name for
A
it?
slab allocator? I haven't heard that one. It might be. I've heard pool allocator. I've heard C++ has one called monotonic buffer. But yeah, there's lots of names. This is the one that I've seen the most anyway. Yeah.
So
Other
doesn't this
question?
get messy with when you're using a library that's not part of your arena? Or I don't know, I guess,
Yeah, that's a good question. Like, if you're using a library that does heap allocations and it's not expecting to be used with arenas, I mean, hopefully, if you're in C, right, whatever the library is doing, it's taking care of its own heap allocated memory however it wants. You could imagine a library that's like, hey, yeah, I'm passing you back a pointer, and it's your problem. I could see that being a problem, yeah. Definitely worth considering. Yeah, any other questions before we move on? This is great. So this is just the basic idea. And some cross-pollination idea. We have the Zig folks next door. In Zig, they actually, if you want to do any heap allocation, you have to pass in an allocator to the function.
Wow.
That's part of the language. And so you'll see here, this might be kind of confusing syntax, but can you see my mouse? Okay. You can see here that they make an allocator that's a testing allocator. They've got a bunch of these. They've got a page allocator, an arena allocator, different things. I don't even know all of them. But then you, over here, to make their array, they actually have to call this init function with the allocator to tell it where it should allocate its memory. And I just took this example because this is actually right on the front page of ziglang.org. This is the code they want you to see, so I decided I'd show it.
I like that defer. That defer runs at the end of the scope then, right?
That's
Is that
right,
what I'm
yeah, so
guessing?
you can see here that this list is being dnit,
Yeah.
but in the arena allocator, it also has something similar, where you have a dinit function that you call, or a method that you call on the arena to free its memory, and you can write a defer statement underneath its declaration to say, okay, the end of the scope, or the end of the function scope, I believe, is when it will do its free. So that's another thing that Zig has similar to Go. We have gophers in the audience. Where are my gophers at? I'm a gopher. Go has an experimental feature to add its own arenas. And this can actually be a super useful way to avoid garbage collection. Because when you use an arena, you're saying, hey, garbage collector, I'm taking responsibility for this memory, so please don't touch it, and please don't trigger while I'm running this thing. And it can be a really great way to get some performance. I did some experiments with this. In some cases, I got 2x speed up, 1.7x speed up-ish on whatever I was doing. Some benchmarks have been a little underwhelming. I actually got way faster results just making an array myself, but it's still kind of useful. So now let's look at some Rust. Finally, let's look at some Rust.
Yay!
So there is a package that you can grab called Bumpalo, which uses a bump arena allocator. And what this does is it's the most simple thing you could think of. It just allocates and bumps a pointer. And that's why we have this Bumpalo. That's their graphic from their documentation. If we look at this example here, you create a Bumpalo bump arena, and we declare it mute so that it can mutate as we add stuff to it. And then in this loop, we're going to add some data to it by using this arena alloc, where we actually put in the data here in this struct literal declaration. And what you get back is a mute point as a mutable reference to the data.
Why isn't it a result type? Because couldn't you technically go past the bounds of like how much memory you've allocated?
So the only way that would happen is if your like machine ran out of memory or your operating system told you you were out of memory. Because the bump allocator is going to reallocate if it needs to.
Oh,
It's,
okay,
it's not bounded.
got it.
Yeah. So then, yeah, you can just do a bunch of allocations on this bump allocator, and then you can call reset. The cool thing about a bump allocator is that, so there are two ways to free memory in an arena. You can either call free, which is like making the syscall to the operating system that says, hey, at this memory address, free the memory and use it somewhere else. Or you can just reset the pointer. It's just like we saw with the stack. That data's still there on the heap, but we just reset the pointer and it's going to overwrite it. And something really neat about Bumplo is that if you call reset, with the borrow checker, it will prevent you from using any of these mutable references that you made before. And I don't know how it works.
Yeah,
if
that was
somebody-
my next
if some-
question is how?
If somebody can figure it, I did an experiment. I was like, really, this works? And I went and did it. And it's like, yeah, like it tells you like, no, you cannot refer to data 1 or data 2 after this because because you called arena.reset or something like that. I don't know why it
Oh,
works.
we gotta figure that out.
Yeah.
I've got to know. I've just got to know.
Yeah, I wish I had a better answer for you guys, but that'll be your homework from here.
Okay.
Question.
So, I'm thinking of that Jurassic Park meme where they're like, they never thought if they like should have done.
Yeah.
So like, so I'm looking at this and I'm saying like, is this something that we're not supposed to do? I don't know. Like,
Yeah,
is it,
that's a
like,
great question. So I would definitely say with what I've looked at, like in Rust, this is definitely this is an opportunity to improve performance in certain use cases,
Okay.
and you pay a price for it.
Right.
Because again, like with Rust, it's trying to do its borrow checking. It's trying to maintain lifetimes statically its own way, and using arenas, you're kind of taking that power from it and kind of saying like I am going to manage lifetimes dynamically, sort of, right?
Yeah.
In this case, it's actually working with the borrow checker in a strange way, but the performance improvements are non-trivial, and I will to put to rest some doubts real quick.
Okay.
I'm just going to show you here. So this is the computer language benchmarks game where they have a bunch of problems where you can submit a solution in your programming language and how fast it ran, how much memory used, etc. This problem is called binary trees, and in this one, all they do is they allocate a huge binary tree that's going to be long-lived, and then they allocate a bunch of little binary trees that get bigger and bigger and bigger, and count how many nodes there are in each one of them, over and over, and then at the very end, it counts all the nodes in the long-lived tree. So this is supposed to be kind of like a benchmark on how good your garbage collection is. And unsurprisingly, the low-level systems programming languages have by far the best performance on here. C++, Rust, they're getting like 1 second. I think Go does this in like 13 seconds, and Java is 10 seconds. It's like no contest. But the Rust solution that comes in second place, right behind the C++ one, uses Bumpalo to do all of its allocations for this problem. And let's just take a look at what they did. They use Bumpalo, and they're using Rayon, so they're using some concurrency as well. And this is a really great example of really understanding what's going on with arenas in Rust. So we have our tree definition here, right? And we need to give these trees their lifetime annotations. And so we're saying, okay, a tree has a left and a right tree that has the same lifetime as the one that is referring to And so then to make the tree, which is down here, we pass in the arena, which is the bump allocator, pass in a depth, and it will arena alloc a tree, and then it will, if it has depth available, it will recursively call the creation function to create the right and the left side of the tree. And you'll notice something really interesting, which is that the lifetime annotation for the arena is the same as the resulting tree. So we've actually encoded with Rust's lifetime annotations that the lifetime of the tree is the lifetime of the arena that you passed into me, right? They're together, which is exactly right, which is exactly the right way to think about it. And then we have this item check, which just takes in a reference to a tree and, checks its left and right and adds up all the things in the tree. Question?
This is maybe side topic, but why can you have a tree inside of a tree? Like, I thought recursive structures like that weren't allowed.
Yeah, isn't that cool? So this works because we have lifetime annotations.
Oh.
Yeah, so your choices when making a recursive structure are do some sort of indirection.
Yeah.
Okay, no, that's all you have to do. If you have a recursive structure, you have to use indirection of some sort. And so you can use a box, you can use a ref count, you can use an arc.
Regular old reference.
Yeah, or you can use a regular old reference, right? In this
That's what
case,
they're doing.
if you use a regular old reference, you have to annotate the lifetime.
Oh.
And in this case, it works out because the lifetime of the tree's children is the same as itself, because every node in this tree has the same lifetime that is dictated by the arena that they were allocated in.
Slick.
Yeah. And so with the bump allocation, with this problem, they're like allocating trees over and over again. In this case, actually all they did was for each tree, they made a new bump, they allocated it, and then they just let the bump allocator go out of scope. And that did the free. I'm actually curious what would happen if they did the reset function, which just like resets the pointer and then just like overwrote what they had. I don't know why they didn't do that, but just another thought I had.
I'm curious if the compiler optimized the recursion, optimized away the function calls or not. Because it seems like
Yeah.
it'd be, for a speed competition, it seems like
Seems like you wouldn't
the
want to do
function call
recursion, right?
overhead would be killer.
Yeah, yeah.
So I wonder if that just got optimized away, or if they tried iteration instead.
Yeah, I'm curious if the compiler has the opportunity to like a const expert it, where it just like inline stuff compile time.
Just out of curiosity, what did the top ranking C solution do?
I'm so glad you asked. I was just about to say.
Okay.
The top ranking C++ solution used another arena allocator in the standard library. That's the one that's called like monotonic buffer. I forget. It's something just so C++. And they also used some concurrency thing that they did. And in fact, all of these solutions that you see on the screen right now use some arena allocator to achieve the speed they did.
What is Rust number 2, Rust number 3?
A different Rust implementation.
Yeah. So on the benchmarks game, you'll have several submissions for the same language. So you can go look at like different implementations in the same language. So I think
this is the fastest like written one we've made or something.
Yeah. This is the fastest implementation in Rust that we
Okay.
have.
Yeah. Remember how I asked? Well, I wonder if they tried iteration. Maybe they did. Maybe it actually ended up slower.
Yeah. So that's actually really fun to go look at all the implementations
It's
for
like
a given problem.
probably this is good practice or something. Maybe.
Right. A lot of times the ones that win out have had to do like black magic to get there, right? Like handwritten vectorization, with SIMD. Some of these problems actually have like rules, like you're not allowed to do this or that. In fact, on this one, if you're a garbage collected language, you're not allowed to use arenas.
Interesting.
Yeah, but if you're a systems language like C++ or Rust, you are allowed to use it.
That's a weird dichotomy.
I don't know why they chose that, but again, it's the benchmarks game. It's all just for learning and fun. Fun fact: Swift does horribly on this benchmark, like horribly. And like Java smokes it somehow, and so that it's one example of automatic reference counting actually getting really hanging up this particular benchmark. Now it's a contrived idea, right? Like, how often are we writing programs that allocate huge tree structures a lot and are like freeing them all the time, right? But it is worth considering, like, am I writing an application that uses big tree structures and does a lot of frees with them? This is one of those things to look at. But again, very contrived, so don't take this as like this applies everywhere.
So we have a question on the Zoom chat that I wasn't watching. It came in about 20 minutes ago.
Oh, sorry.
Yeah, no, you didn't know because I missed it. What happens if the arena runs out of space? I think you partially addressed it. Do you want to just?
Yes. I think he asked over there. So usually arenas have in an implementation something like a standard vector, which is if I run out of space, I just ask for more from the operating system, usually twice as much, and I reallocate everything onto that new buffer.
Okay.
And so you'll be able to allocate to an arena as often as you could possibly allocate at all.
Right.
Like with any allocator.
And then the crow tab dies, goes to heaven.
Yeah. And then
Yeah.
the
So at
crow
some
tab-
point you will have problems,
Yeah, at some point you will run out of physical memory. Yeah.
but it's probably because you did something wrong at that point.
Yeah. Some arena implementations let you specify capacity up front. That's useful if you know how much you need up front, just like a standard vector would. Did you have another?
Yeah. So I've heard that like it's actually a little bit more complicated when it comes to like languages, dynamically typed languages like JavaScript or something, where you ask for, where you go over the size of what you initially want. They'll sometimes do like special like tricks, like 1.5 or something. Like they'll have heuristics on like how to size the array. Would you ever recommend rolling your own arena allocator, or should you always use?
You
like,
can, if you want.
Right?
Okay, let me answer that question. No.
Right. I'm not gonna stop you.
I would never
Because-
recommend that my students do that for any practical purpose.
Yes.
I mean, so I definitely recommend this article. In it, he basically like explains how you would roll your own.
The other answer is, if you get to the point in your career where you know you need it, then sure. But you won't be asking the question at that point.
The implementation was only like 50 lines, so that's why I was asking. It's like, well, is it that easy? So
The implementation
yeah,
of the arena?
yeah.
Where?
Well, didn't you show it? I saw it
I
somewhere.
did not show any of
That
that.
You did not show it.
Usage.
I dreamed that.
I've been
sorry.
showing usages. Yeah, I can't speak to how big. Yeah, I have seen some C implementations that are pretty dang simple. Because it's just a struct that has a front pointer, a next pointer, and a capacity pointer, or a capacity or like length, right?
Well, and some functions too.
And then you add some functions, and all the functions do are, all right, from here, like write this from the next pointer, and then bump the next pointer, right? And then if I'm beyond capacity, then I just run realloc with double the space, right? It's a really simple thing, and it's kind of beautifully simple, honestly. But
I was gonna say, I was curious about the reset, and I pulled it up on my phone, and the entire function for reset is in one unsafe block, and there's a lot of unsafe all over the
oh, I bet.
So,
Okay.
so I think if you're thinking of running your own in Rust, I would probably lean against it. You really know what you're doing.
Hey, unsafe
Sounds
is a perfectly valid part of the Rust language.
And you don't have to wear your seatbelt.
You don't have to wear a seatbelt.
You don't have to strap on a parachute when you jump out of the plane either.
You want speed? Go for it.
It's a lot faster without a parachute.
Let's look at another package that's just out there on crates.io. And this one is called an ID arena. This one was kind of cool. Instead of giving you back an actual reference to the object you allocated, it gives you an ID. And this can be a super useful way to clean up these tree structures that we saw before, right? With the tree structures, we saw that we had to do these lifetime annotations. Well, what if instead we just said, hey, you get an ID? And that's another form of indirection, so we don't have to color our functions with lifetimes everywhere, which can be a pain in the butt. And this is useful too, because it's like, if you have an ID, then in order to find your child or the thing you're referencing, you need to have the arena on hand. So it's like, I have an ID to something in this arena, and so I actually have to do arena.get with that ID to go grab it. I didn't experiment much with this. I don't know how good it is performance-wise, but it's another interesting idea for working with this in Rust. Couple other things. There's a typed arena, which I think got the second fastest on that benchmark for the Rust solution. There's another term called a generational arena.
Okay, hold on. What's
Oh,
Tell
I'm
us
sorry.
about
Let me tell
typed
you
arena.
about that. So the typed arena is just basically everything in the arena is the same type.
okay?
Yeah. I don't think there's much more to say than that.
Okay.
Would you have an idea of what's the benefit of having a single type arena?
I don't know, except that as a programmer, it might be useful to you, right, to understand that like, oh, this arena is only allocating like nodes of this graph, right, and nothing else. Like I'm not going to use it for anything else. All these things go together and they're the same type.
It might help with alignment too. So if you were
It might help with alignment.
It'll help you avoid adding a bunch of padding that you don't need.
Yes.
Right.
Yes.
Also, a common extra usage of that type of setup is to also provide some way to iterate through them all, or maybe search or sort or something like that, which of course is all way easier if it's all the same thing. Right?
Yes. Yeah, I didn't think about that.
Yeah, sometimes they have extra features, and so it's like, okay, that's why.
I think we didn't touch on was what if you want to free specific items inside an arena, and with a bump allocator you can't. Like you just can't. You do not get that.
Free them all.
opportunity. Yeah, you get to free them all or just not free them, because it only knows where its start is and where the next is, and because everything is not the same type as well, it doesn't know where to find the thing you're looking for and free that one thing. And so that's where things like generational arenas come in. I've also seen arenas that use what's called a free list, which they're basically kind of the same thing, which is like I have an arena and you're allowed to free things, specific parts of it, and instead of just erasing that spot, I'm just gonna like
Mark it as empty.
I'm gonna mark it as empty, exactly. And then when you ask for another allocation, then I'm gonna use whatever mechanism using like a linked list that's like, oh, over here there's a free spot for you. Just go overwrite that spot that's been freed up. That's another approach to this. That's really useful in games if you have like a lot of entities. First of all, you want to keep them, we didn't even talk about this, but another useful thing about arenas is that you keep the like allocations together on the heap, and that gives you cache locality. And so,
way faster.
which is way faster. Like going fast 101, put things that go together, because like heaven help you if you need to go to ramp.
Mm-hmm.
And so that keeps them all together. And so, again, with a game, you want to keep them together, but sometimes you have entities that just need to go away, right? Like we don't want to fill up this buffer with entities that don't need to be there anymore because you know the spaceship's been exploded, or it's like gone off screen, and so we just want to free it up. So this is a good use for a free list generational arena where it says, okay, that thing right there, I'm just gonna mark it as it's free. So the next time we want to allocate something, it's allowed to be written over, essentially. And there's a whole bunch of things. It's like a whole world. But I hope that this talk was enlightening, kind of expanded your ideas. Yeah, thank you for listening.
That's AI generated.
No, this was real.
What? That's actually not AI generated.
Yeah, this is real.
So Taylor, have you used any arena allocators in Rust or otherwise yourself?
So I was writing a parser in C
Mm-hmm.
to experiment a bit with this,
Hardcore.
and I used an arena, and yeah, it's great. It's great. One thing we didn't mention is one thing that I did brush up on was realizing that when writing, it was writing a compiler. So I had a lexer and a parser. I didn't quite get to code generation, but I got to the point where I was like, oh wait, what if there's something allocated on one arena and I want to copy it to another arena? Or I have a reference to it, to something on another arena, and I freed that, and I didn't realize that I still had a reference to something there. That was back when I was a little more naive, I guess. But the way that Ryan Fleury kind of puts it is like yeah, just have an arena for your function, and if a function needs to pass back something that's arena allocated, it needs to take in an arena, and then you just you can like organize it that way. The way I was doing it was like, okay, I'll have a lexer arena, and then I'll have a parser arena, right? So that like I can do all the lex stuff, and then after I'm done parsing, I can just free the lex arena, like all the tokens. I can just free those guys together because I don't need them anymore, right? But then I thought like, oh wait, but there's like strings that are allocated over there that I'm still referring to inside the AST. So I might go back to it. That's the only time I've used them like kind of earnestly. But I also did some benchmarks with Go arenas, and yeah, super easy, like super easy to use. And that's just kind of the reason that I wanted to present on this, is just because it's like, wow, this is like a kind of elegantly simple approach to managing a lifetime, and that's something that we all kind of have to work with as software engineers, especially if we want to work at the low level and we want to go fast. So yeah, I'm curious to see what my thoughts would be if I use them more in Angular, especially in Rust, because it seems with Rust you have to play by the rules a bit more, whereas if you're in C, it's like, yeah, sure, man, like,
Do whatever you want.
do what you want.
Seg fault? It's your fault.
Yeah, it's your fault. Exactly. So, yeah. Do we have any other questions in person or from the Zoom?
Nothing from the Zoom yet.
If you have a global like available arena allocator, is that pretty much pointless? Because you're just like
I mean, at that point, you're doing what I said on my one slide, which is just leak, man. Right?
Yeah. Right. So there's no point to that. It always has to be within like a scope, is what I'm saying. So like arena allocators only make sense when you're like passing it to another function or something like that, or you're using it as like a scratch board inside of a function to like build up your work and then pass it off to another arena allocator, or just like completely free it.
Yeah.
So it's kind of bound to like some type of lifetime.
You probably could have a global arena. I don't know about Rust. Rust probably prevents you from doing this because it would have like a static lifetime, I guess.
Yeah, you can have mutable statics.
Okay.
It's unsafe.
It's unsafe.
But you can do it.
Yeah, with your mutable static, you can just have it there and
You
and
shouldn't
just,
do it.
and just fill it up. Just fill up that memory. I'll follow up on this, and I apologize. I didn't go and experiment with this more. I want to know more about this resetting, like just resetting it and like reusing the same arena, even though you haven't like run a free yet, and what the limits are of that. Because when I did that little experiment, I was just kind of blown away that the bar checker was like, yeah, you can't use those things anymore because you called reset. And I was like, what? I'm sure we would all figure it out if we went and read the error message.
Okay, I'm still stuck on this picture because I'm looking in the background. It looks like it's AI generated. That does not look real on the left hand
It's a
side.
little truck.
We've entered a new age, haven't we, where we're just like constantly vigilant about.
Something doesn't look
images.
right. It looks something.
I mean, it could be. I went on Google. Okay.
Yeah.
There's probably at least some like HDR, color enhancement, but.
Well, I think it's just the shape of the stadium that just doesn't look natural.
You know, on these screens, it looks weird. It looks normal on my screen.
No, but like, look in the background. Like, it looks like it's a structure of nothing on the left-hand side. Like, the structure doesn't make any sense at all. It's like this weird,
Well,
like.
these are ruins, aren't they?
Yeah, this is an arena.
Okay.
This is a bullfighting arena, isn't it?
Yeah.
Yeah, but why do they have the weird stone in the back that looks like a
It's
painting?
a wall.
It's
outside.
like it's more of the stands, of the places where people sit. It's more.
This
of
is
it.
gonna keep me up tonight. I'm gonna be like,
I'll send you the link.
it's real.
You can work on that.
Wake up in the middle of the night, you'll
Right.
get it all figured out.
My son's in 6th grade, so we just did a science project. His best friend's science project was, can you tell the difference between these AI-generated
Oh my
paragraphs? That was the science project for 6th grade.
And the teacher's like, wait, all these stories that I'm getting are.
I've heard that basically everything is AI generated in elementary schools or high schools these days. The teachers are using it to make their lessons, and the students are using it to make their assignments. So it's just the AI talking to itself.
Yeah.
Hopefully somebody's observing it, right?
Right. Hopefully they're gleaning something from the conversation.
Oh dear, this is scary. Well, let's move
That
on.
is,
to the
I
next
never
topic.
thought about that. Like,
Yeah.
the teachers are AI generating these lessons. The kids are regurgitating what they prompt.
I remember hearing there was an issue where people would use like Amazon Mechanical Turk to get real people to answer stuff and use that for training for these AI systems. And then someone did some research and found out that a majority of the answers coming from Mechanical Turk were being generated by AI. So people thought they were feeding in like human work, and it was actually feeding, basically
It's closed loop. That's the good way to get.
like ChatGPT for
Overfitting.
itself. Which it turns out is bad. That doesn't go well overall.
Yeah, it makes you wonder if it's going to be a lot harder to train AIs in the future because now there's so much AI-generated stuff out there that the quality of the next generation train is going to be like, what the heck?
It's the self-eating snake.
Yeah.
Well,
There was something on Hacker News about like they're gonna have to set a marker on like 2020 where where you're gonna have to get
That's
your
safe
training data
data.
from, right?
Oh my gosh.
Anything after that is just gonna be bogus, like AI generated nonsense.
Right.
So, yeah, people are just gonna be unearthing like archives from 1950s, being like, I found a treasure trove, it's worth millions.
Well,
It's
'cause
not AI generated.
I certified that this text is all from a library that I scanned
Exactly.
the hard copies.
Like, they were all idiots back then.
Nuts. That's nuts. We got a comment here on Zoom. Any good tools to dump memory and inspect what is happening with a memory management approach? Like
Ooh.
GDB, I assume, but anything dedicated
Interesting.
to memory inspection.
Interesting. Yeah, you got GDB, you got LLDB. They're debuggers. I don't know much else about just doing like memory dumps. Huh? There's
Like
This is that library dumpster dive. I made it
Dumpster
up
dive.
just
That's
now.
not
I
real.
just made it up.
let's ask ChatGPT too.
Yeah, how do we know AI didn't just make that up? Are you just regurgitating? Oh boy.
But yeah, LLDB is probably useful for Rust. It's the LLVM debugger, and it's pretty good. I use it for some things. Fun fact: I tried using a Zig arena allocator to do that linked list. Sorry, the binary trees problem, and I got a seg fault.
Zig.
And I don't know why I got a seg fault. I swear I was checking to make sure that the pointers weren't null before I walked the tree, and I brought it into the LLDB debugger, and
I feel like we need to tell them about this.
I did. I was like, I got a seg fault, guys, and they were like, ask the
Next door.
Discord. It's like,
Yeah, I'll stick with Rust.
So are those, what are those called? Allocators? Are they all packaged with their standard library?
yes, their standard library has a bunch of these, and I was using their standard.
You're talking about the Zig one.
Yeah, so Zig.
Yeah.
Zig. We're talking Zig, not Rust. They have standard library allocators. Yep.
That's crazy.
Yeah, and it's kind of cool because like when you write a function that will allocate, it basically just kind of generically takes an allocator, and so you can pass in any kind of allocator to it. And it doesn't care. It's like, yeah, just give me an allocator and I'll write to it for you.
Interesting.
So
That's
it's an interesting approach.
That's awesome.
It's also useful as a programmer, right? Reading the function definition. It's like, oh, this allocates, and the caller is responsible for its allocations, right? It's a useful thing. Yeah, we kind of get that in Rust, right? With ownership, like, oh, this. What would be the equivalent, like in Rust, like?
Well, if you return a type, an owned type, that means
Right.
it got allocated in some way.
And it's
inside.
abdicating responsibility to the caller.
Right, and
Right.
if that type has heap memory, then it had an actual heap allocation. If the type doesn't have heap memory, then it was a stack allocation.
Yeah, exactly. As opposed to a function that returns like a reference.
Exactly.
Yeah. Although if that reference is something heap allocated, you can't do that. So.
Right, you know that reference has got to be something that came in.
Right.
Because if it's only passing a reference out, well, if it created it, then it went away
Right.
at the end of the function, so
Literally
it
can't
wouldn't
happen.
be able to return a reference otherwise.
Mm-hmm.
Mm-hmm.
Yeah.
This is, I think I know what it is. So you were talking about that reset function.
Yeah.
I think if you call drop on a value, that will know, that's pretty much saying like the
Should we do this?
Yeah, I think it's internally just calling
Should we
drop.
just go find this out?
Let's find it out. Let's do it.
Did I?
But first, let's see if we can find this image. Sorry.
Spencer, come on,
I can't
Spencer.
slip. I
Where'd you
just can't let go of it.
Spencer
Yeah,
is
let me-
really rattle on.
I need to. Did I do
Well,
this?
why'd you stop sharing your screen?
Because I don't want you to like seal my stuff.
Browser history.
Oh, I see.
Um,
Embarrassing stuff. Right? Now you gotta stare at my ugly mug.
Yeah,
Sorry.
I love when people are screen sharing and they like show their Google Mail and you're like, okay,
Let's see.
you're like just start looking
Tell
through
you
their
your
dirty
screen
laundry.
I like when HR does that. That's even more fun. There's an HR meeting, and I'm like, I feel like your outlook is a little more, a little more enlightening than most people's.
Okay, I'm gonna share again.
Okay.
Just screen capture that so
Like,
you
oh,
have some
I have to forfeit my job now because I just showed you all these emails.
Okay, is that like visible?
A little bigger. There you go. Is that big enough for you guys back
Yeah.
there?
That's good.
Okay.
Okay, so this was actually taken from the Bumpolo documentation, and I like screwed around with it. They have this doggo type
Cuteness.
that has a friend.
U64. That's quite a gradation of cuteness.
I know. Yeah, dogs.
Age, however, you.
Yeah.
you
Oh,
only
that's
bits
sad.
for the age.
Oh my gosh.
Yeah, they don't last long.
They
But
won't,
boy, can they be cute.
they won't be living past 255 years. So yeah, so the key is that they have a friend, right?
Ah.
So it can reference another doggo.
Wait, what is a dog? Is it like a
It
dog?
means doggo.
Yeah, it's doggo. It's a doggo.
Okay.
Okay, so what was I doing here?
Doggo.
Can I see a picture of the dog? Sorry.
Spencer,
Generate
come with the
them for you.
pictures.
Okay, so Rust Analyzer is running here. Okay, so it should be working. So I have Scooter, I have Rex, and if we bump reset, wait, this shouldn't work, right? Yeah, okay. So this is saying you cannot borrow bump is mutable here because it's also borrowed as immutable. Okay, let's just like leave here and run and look. So
And this is different. This is saying you can't
Yeah.
reset, not that you can't use your reference after you reset.
right, okay. Oh gosh. Okay, so let's like set this up better then. So we have Scooter. Let's get rid of Rex.
That works.
Yeah.
You got Scooter, and then you reset, and then you try to use Scooter.
Yeah.
And
Now, if we don't use them again, no issues. If we try to use Scooter again, then we get the
Interesting. So it's keeping an immutable borrow on its allocators. Okay, so even though you're making a mutable, go back into your code real quick. So you're making a mutable reference, but what it's actually returning, I think, at least contains an immutable reference to inside the bump allocator. So okay, so they're not actually making it so after you reset you can't use it. They're making it so if you try to use it after your reset, then you're trying to keep an immutable reference across the reset, which takes a mutable reference. Okay, that's interesting. Does that make sense?
Yeah. Okay, so yeah, because reset takes a mutable reference to
To the bump allocator.
And
And
after
your
that-
your bump allocations, your arena allocations, are returning something that has an immutable reference to the allocator inside of it. I don't know if it itself is an immutable reference or it's like a struct that has an immutable reference inside of it. But it's there somewhere because the compiler is
Yeah.
telling us, hey, you've got an immutable reference into your bump somewhere. So you can't take another
Interesting.
reference that's mutable. But you can have any number of immutable references, which means you can have any number of arena allocations.
Yeah, I still don't get it.
They're probably using interior mutability to change stuff or
What I'm
something.
also curious about is if we do reset and then we make another dog.
That should be fine. Because it can
Just-
dump the scooter immutable reference because you're never using it again. Oh, take it back. What happened here?
Sorry,
Oh, was
the
that-
errors don't occur until I write.
Oh, okay.
So yeah, if we make another one and then
That's fine.
talk about them. Yeah, that's fine.
Yeah.
But if we talk about Scooter,
It's gonna be like,
nope. Yeah.
oh, okay.
Yeah.
Cannot borrow bump.
Can't borrow bump as mutable. Because
So
those allocations have got some immutable reference to it somewhere.
So bump is doing something to these things.
yep, there's your homework.
Now, what would be really impressive is if they could somehow get that error down on the top about a scooter line. That would be magic.
Right, like yeah, you can't like we already reset here.
Yeah. That'd be crazy. That's cool though.
Yeah.
That's cool. Just sort of falls out of lifetimes like so much of stuff in Rust.
Yep.
Yeah, I haven't seen a seg fault in my Rust code for like 4 years now. And the seg faults I saw back then were compiler errors.
Yeah, it's nice to know in Rust that seg faults are like an issue to report.
Yeah,
on
it's like
GitHub, right?
it's like a bug in the compiler.
It's
if
a
you-
bug for them, not you.
Yeah, exactly.
Whereas with Zig, I was like, did I screw up or did Zig screw up? And looking at my code, it's clearly perfect. So
Clearly,
it's probably Zig's fault.
clearly, it's gotta be Zig's fault.
Try reporting that to C++, they'll be like, it sounds like a skill issue.
Yeah, it sounds like a skill issue. It really is. Or like, oh, you went into undefined behavior.
Yeah,
That's the
your own
answer to
fault.
every question.
a lot of your own faults in other systems programming languages.
Yeah.
That's why I like Rust so much. It's like, oh, it's not my fault. It's not my fault anymore.
Rust takes care of us.
That's right.
Was it? I want to see that famous Apple one where it's like you're clicking it wrong or something. Or it was. Was it?
You're holding it wrong, the iPhone.
I don't know. Yeah, I don't know. Like it was something like you clicked the thing.
They
the
did an
button
iPhone
wrong.
where if you held it in the wrong place, it screwed up the reception, bridged the antennas.
Oh,
There was a gap in the
yeah.
antennas, and you covered that, it like screwed up all the RF
I
properties of
think
the antenna.
it was if you held it left-handed.
Is this one of the early iPhones? I don't know.
It was
this.
4.
Yeah.
When it was
iPhone 4?
the original
I remember
4
that.
because they put the antenna on the
On that
bezel.
rim.
Yeah, on the
Right.
rim.
I
Oh
remember.
my gosh.
But I think they fixed it like pretty fast.
I mean, who does like left-handed people, right?
Right.
Whatever.
Wait, I don't hold my phone on my right hand all the time. I'm right-handed. I'd rather use my right hand while I'm on the phone.
Yeah.
So maybe it's your right hand, if you hold it in your right hand. Alright,
Well, sweet.
okay, well, anything else you guys wanna talk about?
You guys ready to fight Zig tonight?
Should we go fight them?
Oh, we're gonna have like one of those West Side Story
Is that
scenes?
just-
Are we the Jets or the Sharks?
We're gonna have a rumble.
For a rumble.
It's gonna be a dance rumble though.
We should have like a hackathon with them though.
I bet we could get some AI generated music. Some AI generated choreography for Spencer.
It's gonna be good.
It does feel like your Rust versus Zig dance-off would be a pretty ugly dance-off. Grammars on average or not.
I mean,
My skill set is not to dance.
the rest folks would be pretty nervous, you know, to try and do anything.
But basically, during it, there'll be somebody that's just like, she's like, I'm sitting all day. I can't jump around like this.
Sure.
Well, cool. Well, I think we're done with the main discussion. So, hey, stream and Zoom, I'm going to shut stuff down. Thanks
Thank
for
you all.
attending. We'll see you guys all next month.
Thanks.
Okay. Go ahead and shut